everybody, and welcome to our webinar on the future directions for optical component manufacturing. This is actually the eighth in a series of webinars presented by COBO, the Consortium for Onboard Optics, and sponsored by DuPont Silicon Valley Technology Center. So during the next hour, we'll be discussing innovative manufacturing techniques for future optical components. And when we think about scaling up the manufacturing of co-packaged optics, there are several challenges that have to be overcome, including, how to deal with channel spacing, fiber count, polarization, optical coupling, mux integration, thermal properties. And so we have two interesting presentations today from leading companies in this space. First, we're going to hear from Sven Krüger, who's VP of Product Management at Huber+Suhner Cube Optics Division. And he'll be speaking on the topic of multi-lambda coupling solutions for chip on-board and co-packaged optics. Sven was part of the founding team and executive management at Cube Optics, which is known for their manufacturing of miniaturized fiber optic components, modules, and systems. Cube Optics was acquired by Huber+Suhner in 2014, I believe. Our second presentation will be from Peter Gordon, who's VP of Sales and Marketing at a startup or a privately held company called Cudoform. And they've developed a really interesting technique that involves stamping of metal into micro features and sub-micron features, which would be useful for exactly that, bringing together small optical components. So after these two presentations, we should have plenty of time for questions and answers. Your questions are certainly welcome as we go through the presentation. Please use the Q&A function below and submit your question that way, and we'll address it as best we can at the end. And with that, let's get started. Sven, the floor is all yours.
Thank you, Jim, for your introduction and already this pre-summary on my talk. First of all, thank you very much for giving me the ability to speak here today at the COBO forum. So we are Cubo, and after us there's Cudo, so all very similar but not the same. So I want to talk about multi-lambda coupling solutions for chip on board and co-packaged optics. Jim has already given you a rundown on Huber+Suhner and Cube Optics. Nevertheless, let me say some word on our background. So, as mentioned, Cube Optics was acquired by Huber+Suhner 2014. Huber+Suhner is known for cabling, connector or connectivity solutions. We're into fiber optic transmission since 2000 when we started. And on one hand, we're serving operators with metro transport solutions, so real active or passive systems for metro distances, transporting all sort of data on the other end. And this is where we're here today, making fiber optic components, passive muxes, most of all, and all variants of those, and also optical engines, ROSAs and TOSAs, and the coupling module I mentioned today, being used on chip on board assemblies. Before we go into how we solve the challenges, let's look first back in history. So what are actually the challenges in optics and transceiver optics? So let's look back in history. So around 2010, the dominant form factor was the CFP with 100 gig, and also this variant of LR4 having multiple lambdas, so multiple colors, lasers inside, and four photodetectors. And that was a discrete assembly of multiplexes with fibers and connectors connecting to individual TOCAN-based lasers or photodetectors. And so rather bulky assembly of separate discrete components, and hence requiring a big form factor, the CFP, nicely addressing that, but not the whole industry was overly happy with a big size. And so there was this pressure to make it smaller, so the transceiver had to shrink. And it went around 2015. The QSFP was dominant, and enabling this was to put all these functions of muxing and demuxing photodetectors and that into so-called gold boxes. So integrating it, getting rid of the fibers in between, and having assemblies in hermetically sealed gold boxes, also of the price of a golden box, so to speak. So now, today, there's further integration. So the transceiver size itself is not the problem. It did not shrink anymore. However, as we get to higher speeds, the functionality inside has actually highly increased. So no longer 4 lanes. Now it's actually even up to 8 lanes inside. And there's this tremendous cost pressure. And that required to get rid of these gold boxes and do then also the much smaller in overall size assembly of these photodetectors and lasers directly on the PCB board of the transceiver, so chip on board technology. However, you still need to couple into the fiber and to multiplex. If we look a little bit further, so on the horizon and already starting co-packaged optics. So this is a picture from Inphi that is their design and addressing this requirement with the higher data rates on the switches and routers, that you need to package the transceiver functionality co-packaged to the switch ASIC or near package and all these variants, as this tremendous data rates you cannot transport or not easily transport over the copper lines of your PCB board to the front plate, hence these co-packaged transceiver optics. But now these drive even more challenges. So now you don't have any longer 4 or 8 electrical lanes, which you need to translate into fibers. You get up to more than 1,000 lanes. So that would mean a huge fiber count. And you don't want to handle thousands of fiber on your board. So you can reduce the number of fibers by having multiplexes in that. You still need to couple. And with this approach, you're also now getting very sensitive to polarization. So it gets smaller. So the tolerances, because of these many lanes side by side, they get even more challenging. And as already mentioned, you have with the smaller distances, the channel spacing, so the spacing between photodetectors or lasers has to decrease. So that's driving the tolerances down. If we look on the challenges in a little bit more detail, so as an example, couple light out of the laser or back into the photodiode. As an example, we're looking here at photodiodes. So there are different diameters around of photodiodes. So you can see 20 micron diameter, 2 versions, and a 16 micron PD, or even grating couplers. And then if you look at this active area of these photodiodes, so where they really are sensitive to the incoming beam, and the colors are indicating the different loss levels. So the dark blue would be 0 dB loss, whereas the dark red, you're already in the more than 3 dB loss, so not really acceptable. And so this shows you that 100 gig in the old CFPs, they used typically lensed 20 micron photodiodes. So that gives you what we call a 45 micrometer plateau. So it's actually an effective area where you can successfully with a low loss couple into the photodiode of 45 microns. So it's huge. And there is also, well, of course, with the speed, the photodiode decreases. So, and with the QSFPs, we already see these photodiodes of 20 micron, still 100 gig application. And although it's 20 micron diameter, the really usable area is only 14. And if you go to higher speed photodiodes, 400 gig applications typically used is the 16 micron PD. So that only remains as an 8 micron plateau. And whereas with the grating couplers commonly used with silicon photonics, it goes down to 3 micron. And here it's also very important the angle in which you're using to couple into that. So you see that the precision is increasing the required precisions by magnitudes of order. And while the active area is important, or the precision to get a low insertion loss, what you want to receive, on the other hand, you do not want to have backscattering. So, and this means you want to drive up the return loss as high as possible. So if we look at, this is the example of a 16 micron PD. So if we look on this active area here now, then this would be the same here. And if you go into that PD on an angle of 0 degree, you'd have a lousy return loss. It's only 30, 35-ish dB, and that would not be acceptable. So you need to tilt the angle a little bit of the beam. That, of course, decreases your active area, but only slightly. So you have to find a compromise, but then at an angle of 11 degree, as you can see here, you bring it up, the return loss to around 50 dBs, and you can still have a very good insertion loss performance. So how do we address these challenges? What we have developed is what we call the WDM coupling module, so a multi-lambda wavelengths division multiplexer module to couple into photodetectors or out of lasers. And this is the principle. There are different variants around actually, but showing here a 4-channel version. And you see it's ultra compact. It's about 3 by 5 millimeters and just around 1 millimeter height. And it features, of course, the input fiber. So that would be on a chip on board transceiver. That would be the part sticking out of the transceiver where you connect your patch cord. And then you have this fiber connecting to the module. And then we hand over the beams out of the fiber demultiplex to this PCB board, which is made by the transceiver maker, and that hosts the photodetectors or the lasers. So how does it look inside? Let's have a look through the PCB from the bottom. And so we look from the other end. So here you can see now, this is the input fiber. And we then have a beam bouncing multiplexer setup. So a cascade of thin film filters here. And the incoming light bounces between those filters, and the filters pass or transmit one lambda, for instance, so-called blue or the green, and reflect the others. And so therefore we sort out one by one channel after the other. And then this is focused on the photodetector, vice versa. This could be also a laser, then it's the other way around, and we couple into the fiber. So inside this optical part here, so here's where we do the beam shaping and the steering it or reflection. This is a parabolic reflective optics, which is typically done with a polymer injection molding process. So it's a polymer piece part, and the reflective areas are actually coated with gold to be reflective. And so here we have the filter cascade sitting on a glass block, and the backside is a mirror to work. And here you see the mounting on the PCB board. There's also an RFID chip included that hosts the specific data of that module. I'll come to that in a minute. And what we see as one of the biggest advantages is providing a great performance in terms of coupling and optics, but also a very important thing is the ease of assembly for our customers. So it's basically a very simple 3-step process. You grab that part by a vacuum gripper. We provide the gripper, the tool to align automatically to this coupling module. So you grab it, you place it over your PD lasers, and you find the middle position, and then you put it down, and there's no height alignment necessary. There's an automatic stop by the coupling module itself, and you just glue it to your PCB board. So it's a very simple, straightforward process, which is easy to automate. And here we see how an automated assembly can look like. So here you see the spots of the coupling module of the light on the photodetectors, and we have alignment markers which you can see in your alignment process, in an automated alignment process with a visual tool cameras looking onto that, and you can then auto align. The specific beam position data of each module is stored in this RFID chip. You can load it into your assembly machines and then facilitate the process. Let's have a look on the performance. So this is a little bit showing the precision. So it's the beam positions of each of the 4 beams, the X direction, the Y direction. So here in the X, we're better than 2 micron precision. The Y is even below 1 micron. And more interesting, so the beam characteristics. So we have an extremely flat top bandpass filter. So that is intrinsically coming out of the thin film filters compared to AWGs, so which are rather Gaussian shaped. So we have a real almost rectangular flat top. And typically the insertion loss is much better than 0.5 dB. And it's also very low PDL, around 0.1. And as a summary, this is the whole universe, so to speak, of these different coupling modules. So of course, we're having different photodiodes, as mentioned. So we adapt to the specific photodiodes or to the lasers, and different applications require different amount of channels. So there are different versions around 1 to, well, not necessarily 1 channel, but 2 to 8 channels. We do TX and RX, as mentioned, as separate or combined. There are also BiDi versions, just 1 fiber sending and receiving within 1 coupling module. We adapt to the different pitches. So the photodiodes and lasers, they're not only coming in different diameters, but also in different pitch sizes. Very common are 250 micron to 750 micron pitches. Obviously, then the width of the coupling module changes with the width of your PD array. As mentioned before, we have to adapt the beam, or we adapt the beam angle to the specifics requirements. And it's polarization maintaining, which is a key factor for chip on board designs. And yeah, of course, all the different WM grids are supported by the thin film filters, even SWM, and also just parallel optics. So there's a slightly different version for parallel non-filtered setups. So as last, I'd like to make a small comparison between the 2 technologies that we see around for chip on board. So one is AWG, so array waveguides in glass chips and glass substrates typically, and versus ours. So let's start with the pricing. It's always the most important question. It's a similar cost structure. There is not really a difference. The usability. So on AWGs, this chip, you always need to align in a rather complex assembly process, again with filters with lenses to the fibers, and it can get very critical for small detectors. What we've seen, we have a very simple, depending on the design, you can do a full passive assembly process with these markers. The beam is probably the biggest difference. So we have a real single mode beam characteristic, no Gaussian beam shape, which is slightly multi-mode. Even in single mode applications or especially in single mode applications, that can be a big disadvantage, and very high loss on the AWG side compared to a very low loss on our end and the flat top filter. Okay, I would be happy to answer any questions after our talk. Or you can just write me and contact me later via Huber+Suhner. These are my contact details. So thank you very much for your interest. And I would now like to hand over to Peter not from Kubo, he's from Cudo.
First and foremost, welcome everyone. Again, thank you, Jim, for moderating, Kobo for organizing, and DuPont for hosting our webinar this morning and this afternoon, depending where you are in the US and Europe. And again, I like the theme of today's talk because it involves both the manufacture of unique components, but also leading towards the objective of easing manufacturing for those who use the components to make such systems that Sven has described today and variations on that system. And that's sort of the mission of Cudoform, is to use our prowess and to enable ease of manufacturing among our customer base and to make really innovative end solutions. So we'll lead you through that, and that'll be our conclusion at the end of the talk. So let me begin. And for those who are less familiar with Cudoform, we really kind of combine two unique concepts. One of stamping into metal, and that's the Cudo part, and then accurate shapes, that's the form part for optical components. So it's really a unique small company in Camarillo, California. And it's been at the vanguard of this science and engineering and stamping for quite a long time, and has developed quite a extensive patent portfolio. So the technology is quite proprietary, but it's now being adopted globally. So it's finding areas for easing that manufacturing among many interesting designs. We partner with our customers. It's a very close collaboration involving a lot of engineering services, then the moving to pre-production and tooling, and then moving to production. And that helps us move into volume very quickly, and our customers are fast movers into the markets they're serving. And in general, our tagline is we're shaping light for a healthy and connected world, and using metallic products. And today's talk will focus on the connectivity. So we really do have some fundamental technology here. And let me work you through some of the pictures here to give you a demonstration of sort of what it looks like behind the closed doors of our factory in Camarillo. And we're quite protective of the technique, which has been developed over more than a decade, but I'll lead you through some of the photos. So we do have a unique stamping capability, very interesting mechanical engineering approaches. We do our own reliability testing, so that's looking at the surface finish and the ability of how the form factor played out over from design to manufacture. And of course, we do robust reliability testing too. We have our own optomechanical design team. Some of the software is quite proprietary. We do use finite element simulation. We have our own designs for stamping process, of course, and then we were able to produce quite unique feature sets with a lot of accuracy, a lot of smoothness, and very reproducible. So fundamentally, we stamp metal components with micro features and sub-micron tolerances, echoing Jim's introduction. So the key to this, and I think this is important for the end users, is can we maintain accuracy at scale, right? Can we move up the volume production and maintain the necessary capabilities and feature sets without a cost penalty? And it's quite a unique area that we sit in, sort of the pantheon of techniques out there. But it does demonstrate that we can actually meet economies of scale for high volume production. And we really have fine-tuned micro optics. So if you see where we sit, very accurate, very high production volumes. And it's really a good combination of both without significant trade-offs. We've seen designs that have depended on diamond turning, but when they get to high volumes, they must move on to a stamped metal to really move into the market where they, at the volumes that their end users are demanding of them. So it's really unprecedented accuracy. There's really some interesting microstructures, and it's very reflective and smooth optical surfaces. And you can see we can go fiber grooves and castellations, right? The important cramping and handling of that capability, asymmetrical micro mirrors in arrays, interesting 2D shapes that are unique because they don't require a secondary processing step. And we'll get into that in the future slides of the talk. We are able to accurately create arrays of fiber grooves, and we do teeths in sidewalls. So it's quite unique what we can do in metal with this technique at volume. So let's move on to some of the advantages. And so we take advantage of the metal properties, of course. We'll show later some of the thinness. It's laser weldable, it's solderable, very important for some of the ease of manufacturing requirements. We do plate it. It's rigid and rugged, and it's, again, and Jim alluded to this, and Sven did also, it's very thermally conductive, it's very thermally matched. And again, one of my slides will address that. It really goes to the key point of the talk today, which is ease of manufacturing for the OEMs. We do beam shaping. We can confine and concentrate. We redirect, we expand. We create linear arrays of mirrors. All the things that are important for, again, the pathway interventions that are expected of the optics. And we're able to produce accurate shapes and locations of those shapes, and the ability to put those features where they need to be put within a larger transceiver or other side of the capability. And we lean towards more passive alignment, and I'll address that later in the talk. But again, we're able to enable tighter alignment for the optical fibers, lenses, filters, integrated circuits, and substrates. And as I spoke about, it's very accurate freeform optics. So we're able to do some unique modifications, and that typically comes in early in the process when we are engaging and collaborating with our customers. So we really do produce high quality, and I wanted to show you some slides to demonstrate this. So this ultimately is the surface finish slide, and we really want to avoid secondary processing, right? Because that's an expensive step, and it shows that our SA comes in around 3 nanometers, or SQ about 4 to 5 nanometers, and of course, if you can not depend on polishing, you can again lower cost, but as I've showed previously, you can create some very complex shapes. And again, referring back to Sven's presentation, those capabilities that he demonstrates are going to require some interesting shapes of the freeform optics. So we're positioning ourselves to satisfy some of that demanding technical specifications. And it's all based upon our stamping process. So again, we want to look at sort of comparison of actual to design here, and that the stamping is very consistent. And where needed, where it solves a problem, and that problem will manifest itself in a future slide, it's really a thermal problem. It's compared to injected molded polymer mirrors where appropriate to utilize. So it's quite remarkable with this process that you can improve upon a known capability that's well adopted, but add improved thermal characteristics to that capability, and again enable designs quite quickly to manufacture and in production. So let's look at some solutions that are leveraging this manufacturing capability. So we fundamentally make what's known as a metallic optical bench, and clearly one could do fiber alignment platforms with it. We're doing fiber optic connectors to chips. So we actually can enable vertical coupling without a bent fiber, and that's quite remarkable because as the OEMs and the designers are quite conversant in this area, they struggle with this challenge every day, right? It's less loss, higher reliability, and we'll show you later. It's kind of ultra thin, which has some unique benefits to the solution designers. And finally, in-house, we do some engineering services integration of fiber optic cables just to try out ideas to get sort of that first level look at how the designs will play out and what improvements will be realized. So again, it's quite interesting that we're connecting to optical fibers, lenses, detectors, and silicon photonics. They're really quite suitable to almost any optical connection. So one can see here that independent if it's a 50 micron core multi-mode fiber or 9 micron core single mode fiber, we can connect from the grating couplers to the fiber and from the fiber to the photodetectors. So it's really quite unique how similar technology with some slight design changes and testing could satisfy a lot of known needs right now. And fundamentally, it operates in a harsh environment, right? Again, we'll get back to the thermal capabilities in the slide or two, but I mean, that really opens up the application ranges for solution designers. So now we are going to show that we can do also the global theme of COBO in today's talk. We can do expanded beam capabilities, board-mounted connectors, and then we have other areas that we operate in markets outside of today's scope, but we're actively in biosensing, wearable devices, LiDAR, AR goggles, ultraviolet light for germicidal applications, but they're really all about optical connections. So we really want to emphasize now that edge coupling is now possible with robust accuracy, right? We can demount, decouple, and replace, which is probably three attributes of designs that are like the holy grail, right? So now we've really been able to add some versatility and leverage this interesting metallic stamping to provide some new feature sets. So we're almost there. So here's our thinness slide, and we really look at this. It's really about 0.5 millimeters, but it's quite remarkable. And I think the picture on the bottom is quite telling. That's quite a thin component that has a lot of interesting features stamped into it. So thin is good. It eliminates bent optical fibers. So now you have increased reliability, which we've talked about, but also everything becomes smaller connector heights, right? So now we've streamlined this capability. And an interesting point is is sort of this heat dissipation, right? Because now we can sort of fit this metal optical bench under this heat spreader, so there's no cutoff. You don't have to cut off that capability of that spreader is necessary. So now you have an ability to really ease this manufacturing and assembly and make it less costly. And I think that's going to be a very interesting capability moving forward. The thinness related to ease of manufacturing. So we want to get on in the Q&A because I think when you look at my talk, ease of manufacturing, and you align it with Sven's talk about interesting current and future capabilities that promote easier manufacturing and assembly and looking for solutions to even further ease it in manufacturing, let's go through our little checklist here as sort of my summary slide. So what do we design? What has been designed? Structured metals. So we assert that they're in similar performance to micromolded polymer optics. We've demonstrated complex 3D shapes and microfeatures, and this adds significant value, right? Accurate sub-micron dimensions and a very good mirror surface finish, right? A very small 3 nanometer surface roughness, so the scattering and the loss associated is very low. And if I move that across to the right side of the slide, so the template in general that I've presented today enables visual-based accurate placement and other components, so fiducials, right? The additional features may include a zigzag wavelength separation. Clearly a value looking at some of the slides that Sven shown. We showed a lot of fiber grooves in a very small, thin template, trenches and we call it component pockets. And remember, we don't require polishing, so the feature set could be very complex. What we implemented? Well, we're in a harsh, hot, and compact environments, sort of the biggest global challenge to innovation in this area is dealing with heat. We demonstrated its high reliability and solution robustness. It's stamped aluminum. And it's quite interesting. It has a very low thermal sensitivity and low expansion with heat over a vast temperature range, and enables automatic assembly. That's what's been implemented with these MOBs and MMCs. So let's see on the right side of my chart, sort of go through my superlatives. So there's no mirror deformities due to temperature fluctuations. It is aluminum, so it has excellent CT matching to silicon. Sort of add A and B together, it reduces dependency on costly active alignment. I think most people prefer passive alignment from the point of view of ease of manufacturing and lowering assembly costs. And aluminum is very robust, so it allows solder reflow at 250 degrees. So that, again, that lowers production costs. And it's really a welcome alternative to dependence on epoxy followed by heat cure on the chip package side. So that's my ease of manufacturing summary slide. And I hope it feeds into the general theme that Jim set up for today's talk, which is making components and then enabling OEMs and solution providers to take advantage of them to produce new feature sets, but also lower their own assembly costs. Thank you for your time today, and please contact me with further questions. Please go on our website, and you can certainly reach us in Southern California in Camarillo.
Well, great. First, thank you to both of our panelists, Peter and Sven. We really appreciated that. That's a lot of great material there in your slides. So let's dig into the Q&A portion of our webinar now. It looks like we have probably about 20 minutes for questions. So to our audience, your questions are certainly welcome. Please use that Q&A the feature below, and if you could say who the question is for, either for Peter or Sven, we'll answer as many as we can. So to kick it off, I'd like the two panelists maybe to respond to the others' approaches. I think in this presentation we just heard about stamped metallic approach, and it looks like the alternative is injected polymers that maybe Huber+Suhner is using in their approach. And so I'm wondering, guys, could you work together, or is there a way that these might fit together?
Yeah. So actually, we already know each other and we're working together. I've talked about polymer optical bench, and Peter talked about a metal optical bench, so POB versus MOB. And actually, it's not contradicting each other. I think both have their pros and cons. Peter also showed that the MOBs, they are almost as good as in the surfaces as an injection molded polymer. So, but I still think that the reproducibility of the injection molding is much simpler, and it gives a great surface. However, the great advantage, as mentioned by Peter, is the thermal characteristics. So polymers are more sensitive to temperature changes, so they expand and contract much bigger, wider than the aluminum part. And so if temperature is very critical, so temperature range, I should say, yeah, on one hand. So the range you have to cover, is it from -40 to 85? Then this is a clear advantage, as it will much less expand or contract and stay much better aligned to the rest of this transceiver, so to the grid of the PDs or lasers. And then if you have to get, and maybe also in combination, if the tolerances get very, very tight. So for instance, let's talk about the silicon photonics part. Yeah, so you only have 3 microns. So you cannot move around by 3 microns. Every half a micron counts. So then the metal is an advantage. So in bottom line, we can cover a lot with a polymer setup, but for some instances, the metal is a great advantage from our point of view.
I concur. I think that's a great summary. And again, in the theme of today's talk, our aim is to enable some more complexity that is more stable. And I think Sven is exactly right. Where appropriate, it's a great new technology to deploy. And I think, Jim, you began with this, and it's really where the temperature is a problem, right? And it's becoming a bigger problem every day. Looking at these metallic optical benches could provide an interesting solution to something that can't be solved today. But it's not, and I agree with Sven, it's not a replacement perspective. There's things out there that will require thinness and stability, particularly over temperature, and potentially some interesting features. And the MOB is now demonstrating that it's capable of doing that. So I think its time has come where it's needed, right? And it's incumbent upon Cudoform to produce a reliable device, again, accuracy at scale, and work closely with the OEMs who have unique problems, right? They're solving some interesting problems. So that's where the state of play is, right? It's really now a technical collaboration.
So as you're going up to higher data rates, your thermal variation is going to be, or consideration is going to be more. Is that?
It's not necessarily directly driven by the data rate. It's more driven by what exactly is it where we have to couple into. Yeah. So as mentioned, silicon photonics at the same data rate as a chip on board design is much more challenging. Yeah. So, and they have the same data rate. So one can easily be done with polymer, and the other one we need to look a little bit closer.
Okay. So there's for Sven a couple questions that have come in. Are all the developments related to WDM, or is there any activity in short wavelength modules for co-packaged optics?
Yeah, okay. I saw that question. Thank you. So, short wavelength optics, I could understand as SWDM. And so then it's also WDM, but multi-mode. And actually, we have such a version, but also as probably was meant parallel fiber approaches. So these parallel fiber transceivers. And yes, and then there's evidently no multiplexing part involved. So it's just parallel fibers, each one putting one by one onto a photodetector or a laser. Yes, that was on the left part of one of my slides. There is actually such a design addressing that. But as so far, and this is not necessarily for co-packaged optics, we're working with several guys in this co-packaged optics space, and what we're seeing here is it's still multi-lambdas, but then of course the challenge is not so much that you have just 4 lambdas. They're not using hundreds of lambdas. They still use all the same 4, but then multiple side by side. Yeah, and so then there you have to have a clever way of packaging multiple WDM coupling modules side by side, and then they look slightly different.
Okay. For Peter, here's a question. It's an interesting technology that you've shown. Is it possible to do stamping on polymer optical material? Is it possible to do custom metal patterning on the stamped part?
I would defer to my engineers, but so far we're focused on aluminum yes, we are doing multiple types of customization of the stamp part. So we're really a metallic based, and we're doing some very interesting platforms and micro features to enable alignment and placement. But that's our forte.
I wanted to ask also
we're
about
sticking
aluminum.
with aluminum right now.
Yeah. Yeah. So why aluminum? Is it just because it's softer and you can stamp it like that, or?
I think there's a long history of the company working with it. I think it's a very known material. I think it's known how you can create this technology on that platform. Doesn't mean we can't work with other metals, but in my talk I focused on aluminum, and it has that really good thermal matching capability, right, to silicon. So one could see it as a bench or a platform for those components, right? So the engineers are really sticking with this metal, and they're doing good things with it. So I don't mean to punt a little bit, but we're really metallic, and aluminum is the metal of choice right now.
Yeah, so we want to dig into that one a little bit more. Could you get your slides back up and go back and look at slide 15? So this is also on the CTE matching between aluminum, and the question is whether you've done any, if you have any data or experiments that you've done to validate and or quantify the temperature range and number of cycles before peeling or potato chipping.
Oh, interesting, right? So there's some interesting asks of our collaborative partnerships in this area, right? And it's a little bit confidential because each partner sort of has its test technique for shearing, we'll call it, and other like ferromagnetic capabilities of the device. But I think an email to me with some maybe some request or ask of a particular spec would be appropriate, and then we can get the engineers on it. But we have a lot of experience to demonstrate this. Yes, I just rather not sort of throw out some numbers publicly in how we derive those. But we're certainly receptive to an inquiry.
Okay. All right, great. Could you also rewind, go back to slide number 11? I had a question in there.
Sure. There you go.
Yeah. So on this fiber alignment that you talk about here, I'm wondering if you have any data on that, or any further comments on that, and whether it can be at the same level of precision that Sven talked about in his presentation.
We do. Again, I don't want to seem like I'm deflecting, but we actually have an ongoing project where such measurements are being done for alignment with a potential partner, and so far it's met their spec for what they're intending to do with that. So again, please send us a particular request or inquiry, and we'll take what we can release publicly and send you a response. Or if not, typically we'll go under a non-disclosure agreement and work through you and look at exactly what your requirements are and how we've tested it internally, and what the larger capabilities are. But you're right. Again, I don't mean to defer, but it's in essence kind of sensitive what exactly we've accomplished here.
Yeah. Okay. So Peter, you also touched on the idea of the economics, that there's going to be cost advantages for being able to do this. And I think you showed at the beginning of your presentation just a photo of your fabrication facility in California. So I'm curious about that. If you could maybe characterize, what kind of cost advantages it sounds like these can be stamped out quickly.
That's a good question. Sven and others are quite interested in that answer. So, you remember you're stamping at, and right now the key is that the setup charge is actually quite low, right? So the tooling charge and the time to pre-production samples is quite quick. So that's one component in saving time and money. But the component cost is affordable. There's where we quote volume production moving forward. It's in the range that people would want it to be, and we've gone through some exercises recently to prove that out. So we're not scaring anyone away with the cost of components, but it's really how long that tool lasts, right? because that's part of the long-term production costs. And so far, we haven't worn out a tool. We don't anticipate to wear out anyone's particular tool. We own the tool, right? But I believe that some of our forward-looking contracts show that we'll take on the expense of retooling if necessary, if we're not meeting any agreed-upon accuracy. So that's a pretty good deal, right? So that's pretty nominal get-to-market expense. The component cost has so far shown to be have a receptive audience, and in the long-term expense of retoolings, we take on that responsibility. So it's quite a good deal.
So going back to the module, the WDM module, and the materials that are used for the mirrors, it's the same metal than for Cudoform, right? It's the shininess of the aluminum.
Is this Jim? Is you directing a question to me or to?
It actually, going to be to both, because I think the question also can go to Sven. I think he mentioned that it's gold.
Well, yeah, our main platform, let's put it this way, so it's actually injection molded, so it's polymer plastic, and then to be reflective, we coat it with gold. Yes, so that thin coating is actually metal, but just to make it reflective. Yeah, and I think that this question on could Peter stamp polymers, certainly he could. Yeah, I guess. I mean, it's I've done that in my previous life, so you can do the same things with the polymers. You can use them injection molding machines or hot embossing, as they call it. Yeah, so then it's pretty simple, much simpler than stamping aluminium. However, if you want to structure the polymers, then probably it's better you use the molding and not the stamping. Whereas with the metals, of course, yeah, there's this advantage. So it's, in summary, yes, it's ours is polymer and coated with gold. But as said, there are variants of this platform, different channels, different filters, and also versions addressing much higher temperature ranges. So then that would be with metal. Yeah. So I think there was a question.
There's a question: Is your solution solder reflowable?
Yes, I think John asked that question, and yes, of course, depending on how you process it in which order. So you first do the reflow and then you assemble the plastic. Then there's no issue. But I think John was thinking of first attaching the coupling module to the PCB board and then do a reflow solder process. And if that's at 300 degrees Celsius, then it will not survive unless it features metal mirrors.
Yeah. Peter, any more comments on the mirrors?
Yeah, I think Sven covered it. In our case, it's one step, right? So there's you get it gets the full encompassing the freeform optic, the reflectivity optic, and the platform that it sits on in one stamping step. So that gives you uniformity, consistency, and there's no material mismatch in other areas that could cause a reliability breakdown. So that's sort of our forte, right? Yeah, metal is very productive, right? Whether it's gold or aluminum, and it's just a matter of how you use that productivity and when. I think that's also a theme of today's talk.
All right. Okay, so we have just a couple more minutes for questions. So anyone else in the audience, if you want to get your question in at this point, please use that Q&A function below, and we'll answer it. So since this is a webinar organized by Kobo, Sven, I was wondering if you could share your screens again, your slides again, and go back to one of the slides you showed at the beginning, the slide 4. It's the one that had an Inphi.
Yes, so this is an example of a design for co-packaged, near-packaged optics coming from Inphi. And without knowing much of their details. I think it nicely shows the challenges. At least it gives you an impression, because what appears here to be as could appear, this is one fiber. It's actually not one fiber. These are MTP connectors, so they're you can already guess there are many hundreds of fibers involved, and which need to be handled. And yeah.
So I guess I would ask you: is this merely a conceptual design, or what would you see out there as state of the art requirements now for new switch designs that are coming online? How many of these modules do you need, or how many? What is the expected fiber count that you're being asked to solve for?
Yeah, if we look at the Broadcom Gen 5 Tomahawk chipset, so that's 51.2 terabit per second, if I'm right. So that would mean 5100 gigabit lanes, and so sorry, 500, and so that means then 1,000 fibers, and so. That illustrates. So one big challenge always, or the big disadvantage with the co-packaged optics is it's not really pluggable. So not okay. You could make this part, but this optical engine, somewhat pluggable for the manufacturer of that server switch fabric, but not for the user, because he had to disassemble it. And so there are different versions around. So one idea now is that you have what usually breaks inside a pluggable transceiver would be the laser. So you would have the laser not sitting close to the switch fabric. You have the laser still sitting outside, and then looks like a pluggable transceiver, but it's only a pluggable laser. So you have the unmodulated laser light coming in, and then you have the modulator sitting close to that optic. So, but then you already increase again the numbers of fibers. It's very polarization dependent, and then you have to bring it out again. The light transmit on the receiving end of the same. So it's an endless amount of fibers, and there is only a very small footprint around that. So you have to get very close, and there's quite a high temperature range created by the switch inside, so it dissipates a lot of heat. So in principle, I think this is from looking on high altitude on this is a very typical design. It does not show many details, and then the different concepts in detail, if you look closer on these CPO modules, they vary a lot.
They certainly probably will vary quite a lot. And so I guess the final question here would be, do we need better standards for that?
Oh, from the user point, yes. I mean, it would facilitate our life, because different PD sizes and so on. It's a great variant. However, each of these, the ones who make them the complete CPO module here, they have to provide the PDs or the lasers, and each one of them has different focus or strengths, and so it's better on this PD or the other. So that makes standardization difficult.
Yeah, we've come just about to the end of the hour. Peter, any final comments or thoughts from your side?
Yes, again, thanks, Jim, for moderating. Good questions from yourself and attendees. Thanks, Sven. It's very remarkable that how our alignment is here in our talk today.
Yeah.
Thanks to DuPont and Kobo. And again, where there's some specific technical questions, please reach out to us, and our technical team will get right on it. We're pretty receptive.
All right.
We've seen a lot of these questions, but they're sort of held close to the vest right now, because they're generated, from pretty advanced design teams to us. So we want to treat proprietariness very seriously.
All right, excellent. Well, thank you, Peter. Sven, any last words from you?
Well, yeah, I also like to thank everyone for listening. Any questions, just as Peter said, please address them to me directly or via Kobo. Happy to answer that. And yeah, we're looking very much forward in helping everyone on co-packaging optics or near packaging optics, or however you want to call it. And
all right, excellent. Well, thank you again. So we will make an archived version of this webcast available. You'll be able to find it on the Kobo website and the DuPont Silicon Valley website. And so with that, I would like to thank Kobo and thank DuPont Silicon Valley. And thank you, everyone in the audience, for joining, and have a great day.